Hey, hey, Serena, can you hear me?
Yeah. Yes, I can hear you. Can you hear me?
Okay. Yes, I can. I can see you too. Just to let you know, I made my usual mistake, and I started the webinar instead of waiting until 7. I forgot with a host. I don't need to do that. So there are some people. There are
No
some
problem.
people online already. So, as usual, watch your language.
No problem. As long as you don't mind my dogs banging on the door back here. So.
No, that's all right. I've been online all day, and I've had to send a text to my, teenage / low 20s kids, telling them to stop instead of talking to each other from the same room. They were shouting at each other from like different rooms, and it's like, I'm trying to teach you. So how's it going?
Yeah, it's really just the consequences of COVID and doing everything at home on Zoom. So hey, it is what it is. We're all at home.
I know we're actually having we're hiring we've got a search out for an astronomy professor, and we're having to decide how to deal with interviews. We can't bring them to campus necessarily. They might want to come, and one of the issues is if you're interviewing people in their home, particularly if you're interviewing women, there's a chance that they will have some kid duties, and it's like, it's one thing to say it doesn't matter, but I'm sure it panics the candidate if they get interrupted that way. And so we're having to think about various potential solutions for that, and give them.
Yeah, we are doing all of our medical residency interviews across the nation are being done remotely this year. So it is a big deal. And it's more a loss for the candidates because they don't get to come visit the location and meet the people they could be training with, meet the faculty, and it's been really tough.
That's really important, because if you're trying to get good people, usually they have choices. And of course, at Rice, we feel people from different parts of the country always think of Houston and hurricanes and stuff, and it's when they actually come, they see how great the Rice campus is, but they also see how great the city is and how good the people are, and they're kind of missing out. Plus, we don't know what kind of colleague they'll be. We can see their paperwork, and so we're trying to think of inventive ways to sort of have the more informal stuff, and it's just really a challenge. So anyway, we'll get there. I mean, it's just one of these.
It is what it is.
Things. So you come out of the other end stronger, hopefully.
Yeah.
So are you teaching from home too? You're doing online teaching and.
No, I'm in the hospital, so there is no.
I thought you were doing some teaching as well. No.
So I do. Well, I teach in the hospital. So my residents and my students were on the wards on the inpatient hospital service. Most of my UTB teaching is online right now, unless I travel back and forth to Houston, and then. Most of my meetings are online, but when I go to work every day, I go to the hospital, so I go to work. No kidding, go to work.
Well, good for you.
Yep.
You leave Jeff alone.
Yeah. Everybody's reporting to LSU, and they're all working from their offices. And his class, since it's a graduate class and it's a small class, then it's in person, and he has a lab attached to that. So,
right. Well, the labs make it difficult,
It does.
Do you need to test your visuals to see that everything's okay, or anything special just before we get moving?
Nothing special. I got my PowerPoint pulled up here, and I think all I do is I see the share screen. So let me
if you're host disabled. You should be able to work that. Yeah.
Well, it says host disabled attendee screen sharing.
Okay, so if I do more. Spotlight, make host. Well, I'll tell you what, the simplest way, there's probably a clever way of doing it, but what I'm going to do, let me see what it says down here.
I think you just need to allow it, which is easy to do.
I know, but I can't find that button because it's a webinar format. What I can do though, let me just not worry about it. What I'll do is I'll make you the host.
Okay.
And then that should give you screen. I don't have to share screen, so we don't have to bounce between us.
Okay.
So I'm making you the host.
Here we go. Okay.
Which should allow you to do that.
All right. I see it.
I can see your screen now, yeah.
Yeah, so I'm going to share my screen, and then I'm going to go ahead and pop up. Okay. How's that?
Yeah, it looks good. You want to move that. You want to hit hide on the stop. Well, not yet, but when
Oh,
you get going,
yep.
you'll hit hide,
Okay.
and so it won't block stuff. I presume since this is, I think usually, like if you were in person doing this, we would be making sure we check any videos. But I think since this is on your own laptop and you're just streaming it, I think we should be okay,
Yeah.
unless you want to
Yeah, I
test
do
that.
have a couple videos which I tested before remotely. There's no audio to them, so it'll make it easier.
Okay.
But you'll just see them playing in the background. So hopefully that will work well.
Okay, fantastic. So are you going to be attending? I didn't know if I saw your name. The Space Medicine Summit next week, the Friday. We had a couple of days.
Try. Yeah, I actually want to, because there's a really good Apollo 13 panel, especially towards the end. So I helped Mike Barrett moderate a panel this past week.
Yeah, I saw some of that. I was in the middle of other things, but I did dip in every so often, so that was good.
It was fun. We had a good time. It was a very nice mix of topics that we talked about, and so I'm going to try and join portions of next Friday. When you're on the inpatient hospital service with the residents, you're on for 2 weeks straight. So and rounding starts usually promptly at 8:30 in the morning. So I'll have to figure something out.
You can't pretend you're a teenager and walk the wards staring at your phone.
Nope, can't do that. I actually have to pay attention and make decisions.
Yeah, I should. We're running a symposium in China in the next couple of weeks. I should let you know about that, because part of it is there's going to be a COVID-19 discussion and so on. NASA's kind of funny with China, but anyway, I'll send you the information and
let me know. I'll have to clear it with the agency.
Right.
Yeah.
Well, it's good though. So it's going to be exciting with Shannon and the crew going up pretty soon.
Yes, that's very soon. I have a nice picture of that, actually, just to remind folks that Crew 1 is about to launch. It's very neat, very exciting, and we need to get more people up there, because we only have 3 people right now.
Yeah, I was talking to Kate a while back, because we're trying to do a couple of things while she's up, and just the sheer range and variety of science that is going on, and that one
crazy.
person at the moment is doing it, right? I mean, it's just fantastic.
That's a lot of what I'm talking about tonight. It's really amazing to see the variety.
Right. I mean, she was talking to me about, obviously she's on the biology side and stuff, but she was talking to me about the cold atoms, and I mean, she knew her stuff. It was really cool. So.
Yeah, that's the thing is, I think a lot of people assume that they assigned me to do all the medical stuff up there. It had nothing to do with that. Had nothing to do with the fact that I'm a physician. They're just plugging payloads into a timeline. Science, there's 6 of us, or however many on the U.S. segment, and they plug us in, and we all get generic training, and we're all trained to operate the same science. So you'll have, I mean, it's really, it was just neat, because I think a lot of people, once we get up there, we enjoy a whole lot of different types of science.
Right. And yeah, I know that's one of the things that Kate was saying a lot was, I mean, it's all looking out the window is cool and floating around is cool, but actually getting to do some of this science is great. So.
Looking out the window never gets old, because that picture you see on my screen right there, I took that picture.
Oh,
so
wow. I saw
old.
the movie. I think that isn't that part of a movie, or is that a different time?
Time lapse. They're time lapse.
Yeah, I showed that in my class. I was supposed to do it just get cancelled. I was supposed to do an eclipse tour in Chile for December. But it get cancelled. But there's an Aurora trip for Rice alums to Finland. But I think I missed the bus on that, and of course it's not clear that January or February is going to be safe for travel anyway.
Yeah. The Aurora up there are. I will say that the Northern Lights are absolutely beautiful. It dances. But I will tell you that coming around the south coast of Australia with the Southern Lights, those Aurora are the most beautiful I've ever seen. They're pinks and purples, and they absolutely take your breath away. So we always focus on the green and the Northern Lights, but man, Australia
Well,
was neat.
we have songs about the Northern Lights, right? In Scotland, we have the Northern Lights of Old
Yes.
Aberdeen, and I'm sure in Alaska
Yep.
and various other places.
Mm-hmm.
But yeah, I was showing my class actually this afternoon the aurora on Jupiter and Saturn,
Mm-hmm.
and we've got some really cool radio emission plots that you can increase the frequency into the audio range, and so you can actually play the sounds of the aurora.
Oh, that's
so
neat. That's really cool.
Kind of fun.
That's really cool.
All right, so how are we doing? Well, so we're at 7 o'clock, and we've got about 50 people on who have been hopefully halfway listening to us chat. So let us get the program started so that we can actually have the benefit of our guest tonight. So again, thank you all for joining us. Hope everybody's safe and well and not watching vote counts with too much intensity. It's kind of crazy at the moment. So welcome. We're really happy to have tonight's speaker. Just before I introduce Dr. Ronan Chancellor, let me just remind you, December 10 will be the next and last of the semester installment of the lecture series. And I always forget to look this up before I come on. So I'll have you just keep your eye out for the announcement. We'll start working on the poster pretty soon. And I don't think I've any other announcements, but I'm starting to think and plan for this for the spring. So again, keep your eyes and ears open for that. So I've had the great pleasure of meeting Serena a couple of times when she's been up at Rice. I know her relatively new husband. I've known him a little bit longer. Great couple doing some great stuff, space-related stuff, and also particularly the health-related stuff that we'll hear a little bit about tonight. Serena Onan Chancellor is an MD, MPH, an Associate Professor of Clinical Medicine at the LSU Health Science Center in Baton Rouge. She graduated cum laude while earning a Bachelor of Science in Electrical Engineering from George Washington University, and an MD from the University of Texas Health Science Center in Houston, and completed her internal medicine training at UTMB in Galveston. And then after her residency, she did a second residency in aerospace medicine, which is a kind of interesting subset of the medical field, and spent 3 years as a flight surgeon for NASA before going into the astronaut corps as part of the 20th class in 2009. If I'm reading everything properly, she spent 190 days in orbit, which Expedition 56 and 7, and had a couple of successful, obviously successful, she's still here, spacewalks, which we've been talking about the Aurora, but I'm sure the spacewalks are thrilling themselves. And currently she's got 3 positions, as if she wasn't busy enough: Associate Professor of Clinical Medicine at LSU Health, Associate Program Director for the Aerospace Medicine Residency Program, and also she's still active, even though she's kind of moved over to Louisiana, she's still active in the astronaut corps. And so we're really excited to have you tonight, Serena, and I will now be quiet, turn my video off, and hand it all over to you. So again, thank you for taking the time to do this. And I'll applaud for everyone else since they're not allowed to, so thank you.
Thank you, David. Thanks so much for having me. We have known each other for some time as well. And of course, our mutual friend, my husband, Dr. Jeffrey Chancellor, who, David's right, we do share a lot of the same space interests. And most of the conversations in our home at night revolve around one of the topics I'll hit on tonight, one of our biggest challenges when heading back to the moon and onto Mars, and that's space radiation. And I don't know if you were listening prior to the talk actually starting. I was describing this front picture that I have here on my title slide. And these aurora were absolutely beautiful to watch and even more fun to take time-lapse imagery of. But early in the morning, at least early in the morning for the United States, is when we would try and head towards the cupola to catch a glimpse of these aurora as they began to form. I was up there from June to December of 2018. So I've been back on this beautiful planet for almost 2 years now. So I guess it's been about 22 months. And time has definitely flown. But with that, we'll get started. I plan to talk for really just about 35 minutes or so, maybe 40 minutes, and then open it up for questions. You can certainly, and David, we can figure out how to run that. But if people want to post them in the chat, I can do it that way, or
Well, can I interrupt for a second too?
Sure.
Because I'd like you to hit that hide button so that we don't see that screen sharing.
Oh yeah, we'll do that.
And then I forgot to say this. Thanks for reminding me, Serena. Please put your questions in the Q&A rather than in the chat. That way I don't have to look at two places. And I think if I still have control, when we get to the Q&A session, I will try and unmute you to ask your own question of our speaker. But if for some reason I can't make that work, I'll just put your name up and read your question myself. We'll do it that way. But please wait. Please put them in the Q&A at any time. But we'll start to get to them at the end of the presentation. So thanks for that.
Perfect. All right, away we go. As David said, I kind of fill 3 roles now. This really doesn't add up to 100%. It's about 225%. But I love what I do. I love working in the astronaut corps for the space program. I love internal medicine and I love aerospace medicine. So I've tried really to design a career that fits all 3. So I created it myself and people said, okay, sounds great. So if there are any students out there, whether you're in junior high, high school, college, graduate school, create what you want. Who is it for anybody else to tell you no? Don't fit into a mold. You create that mold yourself. So objectives for today, I'll briefly touch on my background and career path, because a lot of folks do ask me how I got to where I am today. And then we're really going to focus about some of the research. And when I say some, it's impossible to talk about everything. So some of the research on ISS, our path back to the moon and Mars, and one of our biggest research challenges, which is space radiation. There are many, but this is one that definitely hits home for a lot of folks. So my background is, as Dr. Alexander mentioned, I went to GW out on the East Coast in engineering, and then went pre-med I was actually a junior when I decided to go pre-med, and then came down to the great state of Texas and was there for, wow, almost 21 years, where I did all of my training in medical school and residencies in both internal and aerospace medicine. One important thing that I took advantage of was Johnson Space Center offers clerkships for medical students, for undergraduates, and I took advantage of that to learn more about aerospace medicine. And then, as he also mentioned, I became a flight surgeon, which is really just a physician that looks after astronauts and their families. I did that for 3 years. I spent the majority of my time in mission control. This is actually a very, very old picture. I'd say this was 2007, 2008. It's Dr. Rick Shearing to my right, and then our biomedical engineer who sits to the left. So we're the ones that sit in mission control, and we are the advocates for crew health and safety 24/7. So you can see my little cup of coffee sitting there, and I've got all the environmental parameters pulled up for the ISS on one of my screens. So this is actually one of the best parts of being a flight surgeon, was actually sitting in mission control, because you're getting to watch the crew daily, see what they do, and listen to all the comm that goes back and forth. I also spent a lot of time in Star City, Russia, and that's that upper right picture. That was one of the Soyuz trainers that crew would get in at that time. And there's a picture of a Soyuz after it's landed, and you can see its charred hull after it's re-entered. So now I really have kind of firsthand experience of what that felt like coming back in through the atmosphere. But it was a great sneak peek working as a flight surgeon out there in Star City, because I saw how astronauts trained and lived. And then, as David finally mentioned, I was honored to be chosen as part of the 20th astronaut class. Almost all these folks that you see in this picture have flown. In fact, the lady to my left in that photo is Dr. Kate Rubins. She just launched really a few weeks ago to the ISS. She is the sole American on board the ISS. She is an immunologist, virologist. She used to own her own lab at the Whitehead Institute up there at MIT. And so quite well versed in science. I missed her. She tried calling on Halloween, and I missed her call, but I caught her call a few days before that, and we chatted as much as possible, and she loves it up there right now. This is her 2nd trip to the International Space Station. Training for your mission, it's really hard to describe in just a few minutes. I could give a whole nother talk on it, but really it's about putting you in as many uncomfortable and extreme environments as possible to train you what the rigors of spaceflight are like. So I got to go to the South Pole, which was amazing. Again, I could give a 2-hour talk on that. Up in the upper left, that's the big altitude chamber that we're in to learn our signs and symptoms of hypoxia, because we do a lot of training in the T-38 aircraft. And then finally, our big spacewalking suits that you see in our neutral buoyancy lab And I look really, really tiny in that big space suit. And true enough, you are really tiny in that big pressure suit. And that's all to prepare you for the day when you strap yourself into a vehicle and get ready to launch. This was actually just a few days prior to launch. This was our fit check. When you fly out and you launch from Kazakhstan in the Soyuz spacecraft, you have to make sure that everything inside the capsule that's been packed and is ready to go is in its right place. So the crew gets in their flight suit and their suit made for them. You get yourself in, you fully strap in and make sure all the knobs are there, the comm is working. It's a test of the vehicle before they bring it out to the launch pad. The tightness that you see in there, that's how cramped it is inside the Soyuz. It's a camping trip with your closest friends, and it's about a 2-day ride to orbit. You do get out of your seats, of course, you're not in your suit the whole time. And those packs that you see surrounding the center seat, and that's Sergei Prokopyev, a cosmonaut from Russia, those are actually, it's actually emergency equipment with those orange straps in case we land somewhere in Siberia. Of course, to his right is Alexander Gerst from the European Space Agency. So the International Space Station, I think one of the most frequent questions I get, and I'm sure this is a very well-versed audience and quite learned, is, do you ever feel cramped up there? It is huge. So the ISS, of course, is one of the largest objects in the night sky. If you've never seen it pass overhead, shame on you. You should have. There are plenty of apps for that. Pull one up. It is awesome. I think my husband, when I was on orbit, every time the ISS had a good pass overhead, he'd go outside and take a selfie with it and then take that picture, circle him, circle me, and then send it up to me on the ISS. So he knew that he was watching every time I went overhead. But the interior modules that we live in, it's the size of a 5-bedroom house. There is plenty of room. There's room to literally stretch out. Since we work in 3D, you have your own crew quarters where you keep all your own personal stuff. But I never felt cramped. I always felt like there are plenty of places to go. The stack, as we call it, which is those stack of modules you see running up and down in the center, is really long, all the way from the Japanese to the US, the European to the Russian segment. So this is really one of the best engineering marvels of this century. And of course, we are celebrating the 20th anniversary this year. This is the crew that just launched. So you've got Kate Rubins, and of course, they were launching right in the middle of a massive pandemic, certainly not just in the United States, but in Moscow and Baikonur, Kazakhstan as well. Sergei Ryzhikov is the commander in the center. This is his second flight, and Sergei, very popular name in Russia, Kud Sverchov is on the right. This was his first flight. So this is Kate's second, Sergei's second in the middle, and they actually go by Sergei 1 and Sergei 2 on orbit. That's how Mission Control talks to them, but they launched just a few weeks ago. So they are the sole inhabitants of the space station right now. And as David mentioned, this crew is about ready to go in Dragon. Let me tell you, look at how comfy they are in their seats. I am so jealous of their launch position because our launch position in the Soyuz is in the very cramped fetal position for up to 7 hours on launch day. It's actually pretty painful. But the two folks in the middle, you've got Victor Glover on the left. He's a Navy test pilot. This will be his first flight. To the right, Michael Hopkins, who was in my 20th class. This is his second flight. Shannon Walker all the way to the left. This will also be her second flight, long duration. And Soichi Noguchi on the right from the Japanese Space Agency. This will be his third flight, I believe. He's done one prior space station and one prior shuttle flight. So these guys are getting ready to launch on November 14th. All right, so let's go to science. This is what we're going to talk about tonight and some of the research challenges. I bring up the screen because this is an app we have on board the International Space Station. We have tablets that we work on, and the Space Station Research Explorer app, which you can get for free, gives you every science experiment for every expedition and even all the agencies. So if you want to know what science is going on board the space station right now, you can download this app and say, I want to see what physical science is, like Cold Atom Lab. What's going on with that? Who's the PI? What university is this coming out of? What is the purpose of running this experiment? What's the benefit to space? What's the benefit to Earth? It gives you contact information. I really enjoyed utilizing this app up on orbit so I could get a preliminary view of some of the science I was doing. And that's because my crew really wanted to document a lot of the science that we were doing. So we did film the first 8K film on orbit using a very special camera, and we focused on ISS science. So if you've never seen it, just Google 8K video ISS and you'll see us there as we filmed a lot of this. So they kept the film silent. It's more put to music, but I did a lot of individual shots talking about the science. And so this is where I got a lot of my information from. When you look at research on board the ISS, of course, there's several sponsors, from the ISS National Lab to the NASA Human Research Program to our international partners. And when a crew member is doing science on orbit, they rarely know who is sponsoring the science. We don't think about that. Now, sometimes when we're dealing with mouse science on orbit, we do know who the mice are owned by. But really, to us, it's just science. And so we look at the benefits. The Russian research, we do have a little more idea than just a big red ball as to what's going on. I will say that when I was up there, they were actually growing a mouse thyroid gland down on the Russian side. And if you could have watched the conversation that ensued, because they didn't know the English word for thyroid and I didn't know the Russian word for thyroid. So somehow it came out as eyeball. So I thought he was growing an eyeball. Then we realized, no, this is definitely not an eyeball. It's something else. We figured it out eventually. We get along in our Wranglish, as we call it, and we figure it out. We do publish. We focus on publishing. This is a slightly out of date. This is only up to February of 2019. And several more publications have come out since that time. And really, we've been trying to publish in higher tier journals as well. In fact, a couple of articles recently put out were in the New England Journal of Medicine and the Journal of the American College of Cardiology, JAMA as well. So space science gets noticed. And it's, I think scientists and people who talk about or wonder about trying to get their science in ISS wonder if publication is even possible. And yes, it is certainly possible. And it is also spoken about at multiple conferences, whether it's poster presentation panels. There are major conferences that talk about space science every year. The Human Research Program, that annual conference, which is occurring very soon, actually in January. The American Society for Gravitational Space Science, or Research in Science as well, and the Aerospace Medical Association meeting. So several venues where a lot of this is being showcased, easily found online if you're interested. All right, biomedical research. When I talk about this, I think people believe that a lot of the science that occurs on ISS is one big self-licking ice cream cone to further space and space research, when really about 70 to 80% of the life science research we do on board the ISS is for you. It is for human health down here on this planet. So that list I have on the right is certainly not all-encompassing. It's just a smattering of what we are doing on board ISS. And in fact, it doesn't even really do it justice. So when I say cancer research, if I could tell you about the multiple types of cancer research being sent up to the ISS, it would astound you. So let's start with that. This is probably one of my most favorite experiments that I got to do on board ISS. And where I'm at right now is in the US lab portion. I'm at the Microgravity Sciences glove box. This is actually a big encased science glove box where we're able to work with things like cell cultures. So we have the ability to disinfect, to keep things at certain temperatures, feed things into those portals on the side. That whole glove box, I pull it all the way out when I'm using it that day, and then I can push it all the way back in the rack when we're done. So it's really a neat place to work. The first time I worked in there, it was absolutely confusing, mostly because of microgravity. But what you see me holding in my hand is a cassette, a disc of endothelial cells. And this is a project sponsored by a small company called Angiex out of Boston. And basically, they wanted to test a couple things. Their two hypotheses were this. One, that cells would grow better in space than they do on Earth. And more specifically, endothelial cells. Those are the cells that line your blood vessels. They're also, if they're the cells that line your blood vessels, then they're the cells that help create blood supplies. And every tumor needs a blood supply. So this company said, okay, it's really hard for us to grow these cells in the ground. We can't grow them long enough and keep them alive long enough to test our chemotherapy against them. So that if we're trying to create a chemotherapy which kills a tumor's blood supply, we need time to do that. We need to have the cells live long enough to do that. And so that is what they were trying to do. Number one, could we grow those endothelial cells longer in space? And turns out, sure enough, you can. Cells do grow better in the 3D environment of space than they do on the ground. And why is that? Well, the hypothesis is that when you're growing cells in a 2D plate, they're going to grow in 2D. Therefore, the structure and ultimate function or physiology of the cell isn't truly like it is in the body. But when you grow them in microgravity, they, in a sense, believe they're in the body and grow in a better 3D state. They're better structured, higher order, and they more mimic those cells that would be in the human. And the saying is, especially in the stem cell world, better structure, better function. So if you get a cell that more resembles a cell you find in the body, then the physiology of that cell will also more resemble what happens in the body. So this was really neat. I really enjoyed this experiment, and these two videos are playing. Hopefully you can see them. There's no audio. So what I'm doing is I'm working with the microscope on the left, and what you can't see is a video camera above my head that's pointed right at that laptop screen. I'm looking at cells right now. And the PI from AngiX is looking at these cells with me real time. And we are scrolling around on those cells, trying to find examples, looking at different things that could demonstrate their hypotheses. So again, there's the cells that these cassette type things, and in space, everything has Velcro, because if you don't, you lose it. So I Velcro it to my pants. That's how I hold on. And each of those cassettes has varying levels of chemotherapy in them. So I perform media exchanges to keep the cells alive, and then look at them under the microscope, and then look at them with the PI. I probably, for a period of 6 weeks, got to do this about 3 times a week for 3 to 4 hours at a time. And I absolutely loved it. It was a lot of fun to use a microscope again and look at things under the slide. On the right, I'm working in the glove box, and I've gotten really proficient to just be very comfortable with things kind of floating around me, and I'm just letting them hang there. I don't have to keep control of everything, but I'm basically doing a media exchange for these cells. And you notice inside, everything has a place. There's Velcro everywhere. Things do kind of float away, but they eventually come back to their home, and you find them and keep control of them. So it got very, very comfortable very quickly working in the microgravity environment. I really enjoyed this one as well. This was a material science experiment that we did called MIX, Microgravity Investigation of Cement Solidification. And the challenge that we were trying to tackle here is one we're still trying to tackle. And it is, how does cement solidify in microgravity? How does it solidify at varying levels of gravity? And why is this important? Well, if you ever plan to build a habitat on the moon or the Mars, we're not going to bring these habitats up prefab. It's not like a prefab home. We are going to have to create a lot of structures up there. So scientists brought varying levels of water and tricalcium silicate and brought it up there, and we would mix the cement together and then let it harden and solidify, and we'd send it back down to the ground. Just of note, behind my head on the ceiling, that was my crew quarters. So I slept on the ceiling. And you can see the crew quarters behind my back, the 2 little flight tags that you see. But if anybody wonders where we sleep on ISS, it's right there in node 2. But anyway, back to our cement. The other thing we did is we would take these samples and put them in our little tiny centrifuge that we had right there in one of the racks on ISS. And I'd open the door and slide these cartridges in and look at varying levels of gravity. Because again, the moon and the Mars, you're looking at varying levels of gravity. And so they wanted to see what was the porosity inside, what was the microstructure. So this was an experiment run out of Penn State University. And again, I dealt directly with the PIs or principal investigators, and we really had a fun time doing this experiment. So people wonder, how does science even get to ISS? It doesn't get up there by itself and attach itself. It comes up on cargo vehicles. And so the pictures you see down there, that's in the bottom left is Cygnus. And there's actually a Cygnus that just docked a station. And on the bottom right is actually what we see on the monitor when we're docking HTV, the Japanese HTV transfer vehicle. These are cargo ships that bring food and supplies and science to station. So that top picture that you see is capture day. And the guy in the middle is Drew Feustel, and it was his turn, we all take turns, capturing the vehicle. And we do that using the robotic arm. And you can see that robotic arm in that bottom left picture as well. So basically the vehicle comes out to what we call, if you look at the cartoon picture in the bottom right, comes out to a 30-meter high hold. And you kind of see the robot arm coming out of the bottom of the picture there. And the vehicle at that point it gets put into sort of a hover, kind of a very tight hovering position where it's not moving. And using your 2 hand controllers, your rotational and transitional hand controller, you take the robot arm all the way out there and you grab it. And you have about 90 seconds to do that. So we train for this over hundreds and hundreds of hours. So I call it hundreds of hours of training for 90 seconds of terror, because you are the one responsible for capturing this $90 billion vehicle and bringing it safely into station. It's basically just a very, very difficult video game that where you have to fine tune your fine motor skills. But we all captured a vehicle successfully, knock on wood. And this next video I'm going to show you is basically, this was on capture day for HTV. Drew and I were in the cupola looking out the window, and I was just filming with my Nikon D5 camera. And I could film a video, so I did. I wanted to show what it looked like with HTV about 250 meters out from station, and you can see the thrusters firing on the side, the little vernier thrusters to maintain stability of the vehicle. And we were talking about how slow and how big this cargo vehicle was compared to Dragon. So if you're able to hear the conversation, it's not a very long video. It's Drew and I talking about just that.
Oh, now you can see it. Yeah, you can kind of see it swing around.
But compared to SpaceX, I mean,
it's slower.
like more fast.
SpaceX
was like
darkness is coming.
sickness, I think.
Darkness is coming. See the
I know.
creeping over there.
It's like 1/8 of the rate. It's Japanese. It's like
Yeah.
SpaceX was just like whoosh.
Yeah, and this is. Proper work.
So I don't know if you could hear that video or not, but we're just, all these vehicles do a sort of a yaw maneuver towards the end as they position themselves to get ready for capture. And we always felt like SpaceX, and it's the properties of having a much smaller cargo vehicle coming up. It turns a lot faster. And HTV definitely took its time, but it was just a beautiful view watching these vehicles come in and out like it was completely normal. And we did this every day. Parkinson's research, I really enjoyed this experiment. This was sent up by the Michael J. Fox Foundation. They were looking at a protein crystal called LRRK2, which they believe is involved with development of Parkinson's disease. And the reason they were looking at this protein crystal in space is very similar to cells. Crystals grown in microgravity are larger and more well-ordered than crystals grown on the Earth. And so these are some of the crystals that we would see underneath the microscope, and the PIs were looking at us with these, and we'd send them back down. But essentially, scientists, if you can get better insight into the structure and function of a protein, then you can better develop treatment to fight against Parkinson's, or treatment with fewer side effects. So we really enjoyed that. And in line with that, another protein crystal growth experiment was in partnership with the National Cancer Institute. Because you have these gene families that encode proteins for cell signaling. And if you get mutations in this cell signaling, this is when cancer starts. So pancreatic, lung, colorectal. We have no RAS targeting inhibitors in use after years of research. So we basically flew this to the International Space Station just to get a better insight into the RAS gene family, into those protein crystals. Because again, in microgravity, when you look at the scientific reason why, there's a lack of convective currents. So number one, crystals don't sink to the bottom of the plate and get distorted like they would on Earth in a 2D plate, and there's no convection in microgravity. So these crystals just grow a lot better. This was a really neat experiment out of a very small company called LambdaVision, where they were trying to create retinal implants for a condition called age-related macular degeneration. It's very common. That bottom picture you see on the right is what happens when you have this condition. You begin to lose your vision right in your central field. It's devastating. It happens in our elderly population, and it debilitates people. And there is no cure at this point. So this company believed that, hey, we have ideas for our manufacturing and our assembly of these tiny, tiny layer by layer, thin, multiple layers of basically bacteriorhodopsin. And what they said, or what they thought, was that they thought was interfering with the uniformity amongst the layers. So for them, it wasn't that they were producing something on orbit that they would make 100 times, then bring back down to Earth and use, but they wanted to study the layering process by eliminating gravity to see how they could change their manufacturing processes on Earth. So to me, that was actually really fun. This was one that we did not interact with directly as a crew. We generally would install an experiment like this in a rack, and then they could operate it from the ground. Tissue on a chip. This, I really think, is going to be a huge part of the future of ISS. So basically, tissue chips in space was initiated in 2010 by the NIH with the FDA. And also the National Center for the Advancement of Translational Science. But basically, you're trying to take an organ or a mimicker of an organ in the human body and put that on a tissue chip. So why would this be useful? Well, instead of using certainly animals or humans to test candidate drugs, vaccines, or even biologic agents or drug toxicity, wouldn't it be better to test it on an artificial model of that? So lung on a chip, kidney on a chip. What if you had, they actually called their model chip, what if you had multiple chips all put together mimicking the human body? I know that sounds almost ridiculous and maybe hard to do, but we have already sent tissue chips to the ISS. As an astronaut, I look at it this way. I say, hey, if I could find out an astronaut's individual sensitivities, let's say to space radiation, to osteoporosis, to forming kidney stones, if I took tissue chips, let's say 20 tissue chips from astronaut 1 and another 20 from astronaut 2, and sent that up to station years ahead of when they would fly, it would give me individual information about that person to basically create a precision medicine platform. So when they do go to ISS, we can better protect them. So it's not to eliminate people, not to see who's weak and who's strong. It's to say, okay, astronaut 32 might be a little more sensitive to bone loss on orbit. So do we consider more preventive measures? Do we consider pharmacologics before they go? So I really see this as the future. It's like getting a little bit of insight into how an individual's human system works before they actually go into space themselves. Okay, so let's talk about the future. If you all remember, Vice President Mike Pence, at least current Vice President Mike Pence, they issued Space Policy Directive 1. And basically, NASA was charged with landing the first American woman and the next American man at the South Pole of the Moon by 2024. And with the hopes of that we would have a sustained presence by 2028. If you look at your calendars, that is not that far off. It is almost 2021, folks. And unfortunately, the pandemic has certainly hampered things to a degree, but NASA is pushing forward with this goal. So phase 1, really to get boots on the ground. So minimal sustainable architecture. You're not going to have big lunar habitats by 2024, but just boots on the ground by 2024. But by 2028, not that much longer, could you begin actually having sustainable lunar habitats? So if you've heard of Gateway, Gateway is, in a sense, our space station around the moon. And we would be working towards, if you look all the way across this graph to the right-hand side to Artemis 3, crewed mission to Gateway and the lunar surface. So Gateway would orbit around the moon, and at the right time, we would do 30 to 90-day sorties down to the lunar surface, or several sorties over a 30 to 60 or 90-day period down to the lunar surface, and then begin building our infrastructure. So a lot of people say, why on earth would we go back to the moon when we've already been there? We've learned all that we can learn, and it seems pointless. Well, that's so that we can go here, because let me tell you, you don't want to set off for this planet until you really have your ducks in a row, because now you're very, very far away from home. So we use the moon as a test bed to test the robustness of engineering, infrastructure, the human system alone. It's one of your weak points. Comm delay, you name it. There are hundreds of different things that we can test and try out on the moon before we head off for the red planet. What I have listed here is just a few of what I consider some of the biggest challenges. Of course, I'm a physician, so I always look at the medical side of things, but radiation certainly is one of your biggest. It is one of NASA's top challenges, one of their biggest gaps, especially for the human system as we head back to Mars. But you look at some of the others listed here, and what about pharmaceutical stability? We have no CVS or Walgreens on the way there. How long do drugs actually last once you take them off the shelf? Let's say a prescription for antibiotics. Is 6 months past that expiration date okay? Probably. What about a year? What about a year and a half? How are we going to resupply up there? Bone density, I think, is a huge issue. There was actually a paper that came out of PLOS One not that long ago, about a year ago, written by folks out of Ames, which looked at, used Monte Carlo simulation to look at predicted bone density loss on a 3-year mission to Mars. And it's impressive. It's a lot of bone density loss. What we're able to do in ISS today is not what we're going to have as we head to Mars. ISS, we are, in a sense, very spoiled. We have no comm delay. We're close to the planet's surface. We've got the best countermeasure suite to maintain bone and muscle mass available. We're just not going to have that as we head back to Mars. Or not back, head to Mars for the first time. All right, so let's talk about space radiation. And I proudly say I steal most of my slides from my husband because he makes the best slides when it comes to space radiation. Space radiation, it's one of the most difficult topics to understand, I think, in the agency. And I've sat in many meetings where you have upper level management, engineers, scientists, and physicians, and it is still confusing to everyone except for the space radiation expert. So space radiation is direct ionizing radiation. Certainly you all have probably heard about galactic cosmic rays, which are present. I mean, we experience galactic cosmic rays here on the surface of the Earth, just not to the same extent that we do up in space. Solar particle events, solar protons, and of course, trapped radiation in the belts. I love this picture because if you ever saw the TV series Chernobyl, which came out, a year ago, it really portrayed this. If you ask anybody in the astronaut office, how do you view space radiation? It's this very bleak, dismal, unknown threat that's out there. And we don't really know. It's hard we can't see it, obviously. We know it's there. We know it impacts us, but we really don't know how. And I think the biggest question that's out there is, hey, can the human at some point fail from space radiation on a mission? How do we determine that? How do we look at space radiation and the science and the experiments going on and translate what we see into clinical effects on humans? How do we do that? It's really difficult. We're not allowed, at least certainly not in the United States, to just take humans and irradiate them to see what happens. Most IRBs would be firmly against that, as would anybody with ethics. When you ask the astronaut office, how do you view radiation? The crew will ask you, okay, I know with radiation, just tell me how many more safe days in space do I have based on my career dose so far? How long is my career going to be? How many more days can I go back into space? And we say, well, that depends. Depends on how long you were there, depends on your age, depends on if you're male or female, depends on the solar cycle at the time. But this is what they care about. Every astronaut's going to want to explore. Right? You almost have to protect them from themselves, and certainly when it comes to space radiation, because it is so hard to quantify and so hard to understand. So if you look at dose as to how much we're getting, certainly on an average ISS mission, average dose is, again, it depends on the solar cycle and a lot of other factors, number of spacewalks. Here we have listed under ISS about 75 millisieverts. I think mine was definitely over 100. But look at the projected dose for a 2.5-year mission to Mars. And what kind of also puts this in the question is, think about when you're in the ISS, when we're in the ISS, we are well protected from space radiation. We are protected by the Earth's atmosphere, by the geomagnetic field, by the shielding itself of ISS, at least 15 to 20 grams per centimeter squared. We're not going to fly a vehicle out to Mars or to the moon with 15 to 20 grams per centimeter squared of shielding. We don't have that lift capability. Now, once you leave the protection of low Earth orbit and head to the moon or back to Mars, what do we have? I mean, it's significantly less. So definitely the threat increases here. Now, I think we don't give the human body enough credit in that the human body can really tolerate very low dose exposures of many things for long periods of time and do just fine. We have humans who live in very high altitudes. We have humans who live in very polluted environments. And the human body adapts to these very low dose insults. And so I think the human body actually does really well with low dose rate radiation. Now, how that changes on the way out to Mars is a different story, and it's something we have to look at. So this was actually a small video I shot using one of our radiation detectors that we have on board the ISS, and that's the Timepics detector. And it's basically a little USB stick that I stuck in this computer in the cupola. And here you can see the ISS. If you look on this map, see this hashed area. And that is the ISS traveling through the South Atlantic anomaly, where the dose rate goes up tremendously. And so you see the dose rate, it's a little blurry, but it's here, and it's gone up by a factor of, I don't even know, but it's huge. And so I kind of filmed this sitting in the cupola. My husband asked me to do this because he's trying to explain to people how much the dose rate goes up when we're traveling through the South Atlantic anomaly. And that even impacts some of the science that you're doing. We did science on orbit looking at human and bovine sperm. And the PIs wanted to know if we were doing some of the science. Oh, so that's looking at our beautiful Earth. And that's actually Cygnus, our cargo vehicle docked right next to the cupola. But that's the view I got to see every day, which was fantastic. Those big plastic shields you see are actually protecting the windows of the cupola because we were getting too many scratches on the cupola from people taking pictures. So, but anyway, back to the South Atlantic anomaly. When we had science going on board ISS, that science or biological science that might have been sensitive to that increased radiation, they'd want to know exactly the time points of when ISS entered the SAA and when we had their science out in the open of ISS. So they keep track of all these things. It's very important. Oops, here we go. There's a lot of existing research out there right now, and I think people don't know how to interpret this. They look at, this scientific reports article that the lunar astronauts had a higher rate of cardiovascular disease mortality, maybe from the ionizing radiation of deep space. This article was actually countered pretty well not that long after because for a number of reasons, but you also have to understand that Apollo lunar astronauts still smoked a lot and had a lot of varying risk factors that also contributed to cardiovascular disease compared to today. But some of these other articles that came out, they were looking at what happens to your brain on the way to Mars? How does radiation impact neurocognitive function? What's your risk of cancer? Well, all these experiments are done on animals because it's the only thing we have down here on Earth, animal models, to test the space radiation environment. So then this is the really hard part. And my husband's very proud of the slide, only because I come right after the pig. But what we test space radiation on are radiation mimickers, are mice, ferrets, pigs, to try and determine what those clinical effects are. And then the hard part is making that jump to the human. So there's huge uncertainties. We are not pigs, we are not ferrets, and we are definitely not mice. And the more higher ordered mammalian species, like a human, has amazing adaptive and repair mechanisms. So that's why I like tissue chips so much, because my thought is, could you take tissue chips and begin to maybe predict a little better some of these clinical effects? I think we will always continue to use animal models for the space radiation environment and for that research, but there are tremendous limitations. And their physiologic processes and the way their body handles large doses, let's say of space radiation, is completely different from the human. And so it's really hard to make those leaps and then publish it, and then people don't know what to think because we've had not a huge body of experience, but a good number of flights now where folks have flown for up to a year, and we are not seeing these effects that these articles are talking about, let alone the risk of cancer, which is another lecture in itself. You talk about the risk of space radiation and the potential cancer risk. So, but with that, it's just about 7:45, and I do want to give some time for questions. So I'll show this final slide. This picture was actually taken on the day that a Soyuz, for the very first time in history, aborted on launch. So we had two of our friends who were supposed to join us in October of 2018. That Soyuz launched from Kazakhstan. There was a failure of the first stage as it separated from the rocket. It came back around and struck the rocket, causing it to go off axis, and the automatic launch abort system activated and saved the life of the crew. First time it's ever happened in spaceflight history. So they parachuted down quite unexpectedly. And then we realized, Sergey and Alex and myself, that we would be the only ones on ISS for the next few months until the space program, both Russian and American, figured out how to get someone to us. And people were really worried about our well-being and our mental state. And so we said, you know what? We've got food, we've got air. This is our home. So we put our home t-shirts on and took this picture to send down, to send back home so that folks wouldn't worry. So with that, David, thank you so much for having me again. I've always really enjoyed this lecture series, and I'll do my best to answer whatever questions you have thrown out there. So let me stop sharing. And let's see here. Actually, hey, David, do you know how I...
Yeah, I'm trying to find out myself.
I think I made it.
I know
I hit it, and
there's a stop screen at the top.
It is. Yeah, I'm trying to get it to show up at the top. There's nothing that's popping up here. Let's see. Well, let me end the show. Let's do this.
Yeah, but it should be.
Oh, here we go.
Okay.
There
we go.
I had to get back to where you were. Stop sharing. Okay, I'm not sharing anymore.
Okay.
Sorry.
Well, thank you very much. That was good. We have a few questions. A lot of them from Hongyi Zhang, but one of the first ones, just to get out of the way, I'm going to read them in order, but there was one that comes up from Hongyi, basically saying, could you just tell everyone what do you mean by microgravity? Just because I think that may impact some of the other answers. Just yeah.
Remember that with physics, the ISS is actually in a constant free fall around the surface of the Earth. So if you look at, we kind of interchange the terms zero gravity and microgravity all the time. If you really were to measure it and look at the physics of that, it's probably not zero exactly. It's very close to zero, hence the term microgravity. But essentially up there, eliminated. Oh, my husband just shouted at me from the living room and said, it's still zero gravity.
Tell him he'll have his day some other time. I'm tired of hearing from him. So tell him to.
David says you'll have your day some other time.
I think he can hear me because I think he is online actually.
He probably is.
Hi Jeff. So well, thank you for that. So Sheena W says, good evening, Serena. Just wondering if you could think of one extraordinary thing that humankind is benefiting from today as a result of your research on the space station, what would it be? I think that's a kind of nice question. Actually,
that's a great question, Sheena. Thank you. I honestly think that the field of cancer therapy and cancer therapeutics and immunotherapy is exploding. If you look at big pharma, even AstraZeneca, GlaxoSmithKline, a lot of these companies who are creating basically biologics to help treat cancer. And biologics are basically medications that take advantage of your own immune system to treat cancer, which is the emperor of all maladies. They are taking their medications up to ISS to better formulate them, better learn about their structure. They've looked at nanoparticle drug delivery as well. So I think I'm most proud of the small part, and granted, we certainly can't take tremendous credit, but the small part that the ISS is playing in the field of cancer therapy, because there is no other platform on Earth that can do this or mimic this, because there is no, and I get this question sometimes, where's the zero gravity room on Earth that you use to test things? You know, can't you just do this on a zero gravity airplane as it flies tons of parabolas? You can't. You can only do a lot of these studies at ISS. So I think that's one of the biggest contributions.
So thank you. So as I've mentioned, Hongyi has asked a bunch of questions. So what I'm going to do, just to kind of share the wealth a little bit, is I'm going to bounce between the questions there. So I may not put them all up at once. So one question is, are the astronauts in ISS all scientists specialized in different subjects? Generally speaking, how can a scientist become an astronaut?
Yes, the answer to your first part of your question is actually no. So I flew with 2 geophysicists, a teacher, a test pilot, and an engineer. So when people come into the astronaut corps, they come from a variety of backgrounds. In my class, we had Navy test pilots, Air Force test pilots, flight test engineers. Kate Rubins was a virologist. Jeanette Epps was an aerospace engineer. I was a physician. They bring you in and then they equalize you across the board. You're all trained how to do spacewalks. You're all trained equally how to do science and how to perform science. You're all trained how to do robotics. So we don't get specialized tasking on an ISS mission. They want you to be certified in every area so that no matter what, they can fly any combination of a group of people, and people are switched out and switched around all the time, and everybody can get the job done. Hopefully that helps. So a scientist can become an astronaut just like any other profession can. It's exactly the same path.
It's tough though.
It's very tough.
And you can't be too tall, I'm finding. So
well, and I will say, David, also
I
get from graduate students is, should I get my PhD? And my answer is absolutely yes. So if you have a dream of going in the astronaut corps, get your PhD. You need your advanced degree to be able to do this. And they want someone with an advanced degree who's also been out there in the field and done work and research in whatever their area of expertise is.
Okay, so I'm going to jump to Blanca Behar. What is the lifespan of ISS?
Ooh, I hope a really long time. Now, I think at some point, we're going to be we have these private astronaut missions. They're going to be coming up to the ISS. We're going to have more commercial companies possibly adding modules onto ISS strictly for science. So I think I'd love for it to be another 20 to 30 years. I don't know if it's going to last that long. It is an old house. We are constantly, a lot of our days were spent doing science, but a small portion of our day was always on preventive maintenance and upkeep of the station. So we replace parts before they break. We don't want them to break and have major systems shut down. So I'm going to say I hope for a really long time.
I'm going to jump to one of our professional master's students, and I'm going to criticize him for his question being so long, but I'll read it all anyway. Robert. This is from Robert Bullard. So regarding the risk of orbital debris to both crew in a craft like the ISS and scientific instruments on satellites, where are the gaps in what NASA/DoD can observe and track with ground-based telescopes and radar? Also, who/what group is at the cutting edge of solving the challenges of managing current orbital debris and what measures are being considered for remediation of orbital debris in the future? So it's a big general question about orbital debris. Where are the gaps and how are we handling, how are we planning to handle it?
Yeah, so I think, with the risk of orbital debris, NORAD themselves, we have NORAD tracks that can track orbital debris up to a certain size and probably smaller. They're just not telling you what they are able to track. Funny story with that, when I was on board ISS, I actually ejected a very small tool out the Japanese airlock accidentally. It was a tool that wiggled, it was actually a ball tip hex head that wiggled its way into a payload. And when they basically launched that payload out the little tiny Japanese airlock, they saw the tool coming out with it. And that little ball tip hex head now has an orbital lifespan of about 2.8 years. So I told them they should name it after me, and sorry about that. But with that being said, I don't know where the gaps are with NORAD. NORAD is really good at what they track. We actually have a specifically designated position in mission control called TOPO that tracks everything. And if we think we're going to have a conjunction, at least that's what we call it, or something may hit the ISS, we label it as green, yellow, or red, and we can actually perform a debris avoidance maneuver or a dam to get the ISS out of the way. Now, unfortunately, we have been doing more and more of these debris avoidance maneuvers, which is basically we're raising the altitude of the ISS, right? We're doing more and more of that recently because there's a lot more debris out there. So how's it being managed? I actually know of one cool Japanese company called Space Sweepers, where they're trying to come up with methods to begin ridding low Earth orbit of this orbital debris. Now, I have not seen anything put into action as of this point. So as of right now, if you were in the cupola and looked, you'd see tiny dings on the windows of the cupola and on the handrails all the time. We get hit with little tiny pellets of orbital debris all the time. So it's out there, and unfortunately it's getting worse.
Yeah, we just had Mark Matney from the Space Debris Group at Johnson give our seminar for the Professional Masters program just on Tuesday there. So lots of it's a big issue. So again, there's a couple of questions from the same characters. So let me go to Hong Yi again, and then I'll jump to someone else. The US has achieved sending astronauts to the moon in 1969. What are the difficulties in sending astronauts in 2024?
Oh, that's easy. Money. So NASA had 8% of the gross domestic product back during the time of the Apollo program. We had the money and the political motivation to go to the moon because we wanted to beat the Russians. And we had the Apollo program. We had the Saturn V, heaviest launch capability in history to date. A lot of folks believe that if we were not in a political race with the Russians to get back to the moon and that the entire country wasn't behind us, that we would not have done what we did back in 1969. There were a lot of reasons for that. So nowadays, we're building a new rocket to do this. We have to build a new lander, basically a new human landing system to go back to the surface, and then a new habitat for the astronauts to live in, because we'd like to establish a permanent presence. So a lot of challenges. 2024 is ambitious, I will say that, but we're working hard to get there.
And then we have one from David Guajardo, actually two questions. For how long does the EVA astronaut, EVA astronaut have to pre-breathe 100% oxygen before going out of the ISS? And did the cosmic rays ever wake you up? And often do you see them?
So interestingly, we would see, I'll answer the second question first. And although my husband doesn't think that what I was seeing were high energy or high particle events, he argues with me on this one. We would see a phenomenon where if our eyes were closed, we would see very bright flashes of light out of the periphery of our vision. And we knew we were seeing these because a couple times the crew, if we were listening to music and 2 or 3 of us had our eyes closed, we would all see the same flash and wake up and comment on it. It happened to shuttle astronauts a lot, and it was probably the orbital inclination at which it was occurring. On ISS, I'd say 2 or 3 times a week when I'd go to bed at night, I would see these flashes, and it was very bright. It was almost as if your eyes were closed and you were standing by a window and a bolt of lightning hit. It was that bright, and it would make you wake up. And then his first question, what was the first part of that question, David?
About pre-breathing 100% oxygen.
Oh, pre-breathe, yeah, that's a really good question. So we have different pre-breathe protocols. The old protocol was you'd breathe 100% for about 4 hours. It was an in-suit pre-breathe. Talk about being in a suit for a long time before you even get out the door. Now we have what we call the aisle pre-breathe, the in-suit light exercise pre-breathe protocol, which shrinks that time and begins that washout period of nitrogen by performing very light exercise inside the suit while breathing that O2. So it can vary. We've got different protocols, actually.
Okay, so I'm going to jump a couple and then I'll come back to Hong Yi. But Jared Taylor asks, besides space radiation, what are the biggest advances we need in technology/knowledge before a Mars mission? If you were going on that, what would your biggest concern be?
Actually, a working toilet. These are simple things, but I just saw Mark Jernigan pop up a question. Hello, Mark. It's good to see you.
Yeah, there's a couple of insiders coming up.
I know, lurking around, but it's good to see them. And I'm serious about the toilet thing. You look at the robustness of our engineering on board ISS, environmental control and life support, water reclamation, the toilet. These things break down a lot. We're doing a lot of not only preventive maintenance, but we were constantly repairing these. So I really like to make sure we have a good system in place before, no kidding, we head off to the red planet, because every time the toilet breaks in ISS, you've got this massive crowd of people with cameras and instructions and locations of equipment and all the help you could possibly need and no time delay. Now you're 4 months out to Mars. Now what are you going to do?
Take a plumber.
Yeah. So anyway, Oh, and that's Jared from the Spartan Lab at LSU. So thank you, Jared, for the question.
Right, a lot of good people here. So go back to Robert again. The scientific case, what is the scientific case for crewed missions to Mars versus robotic exploration? What are your views?
Yeah, so I don't think it's one or the other. I think we have to use both. I think there are going to be certain tasks where we can use robots to enhance what we do, but robots are definitely not humans. So at some point, human beings have to push past low Earth orbit. We have to be able to colonize and live on a planetary surface other than our own. And it's not just for the romance of it, it's for the sheer reality of it. We have to continue to expand as a species. I think robots will be with us every part of the way. I think they'll be helping with exploration and mining and excavation. I think people believe we have all these robots assisting us on board ISS, and they bring new ones up all the time. We mostly just giggle and laugh at them because they float around and follow us, but they don't really do anything. So until we're there yet with the engineering technology of robots, I'm not terribly convinced, but I do think we'll use them a lot in the future.
Okay, so let's jump to the couple of RSI, Rice Space Institute insiders. So we'll start with Mark, since he kind of popped up first. So Mark Jernigan, who is currently our Associate Director for Special Projects. He says, hey, how many organ tissues have been grown?
Ooh, organ tissue. So, we've looked at organoids, certainly brain organoids. We've looked at cardiac stem cells. They've tried to grow
Mark could do with the brain organoid, by the way.
Maybe. And that's actually one of the neatest things about stem cells and microgravity is they found that the cells they grow in microgravity do better resemble cells that are grown in the body. So luckily, a lot of those experiments started right after I got up there. I was a little jealous of the folks flying after me, but certainly brain organoids, we've looked at cardiac stem cells, mesenchymal stem cells. The Russians have grown that small mouse thyroid over on their side of the house. I'm not sure about the quality, but this is going to be a big part of us pushing forward. Stem cell research on board ISS is really taking off.
Okay, I'm just wondering how much time you have, because we've still got about 11 questions.
I got another 10 minutes or so. We can do another 10 minutes or so.
All right. Well, let me ask Professor Reif's question. So this is Patricia Reif, who is the current Associate Director for Outreach at the Space Institute, but was the actual founding director of the Institute. She was the one that got it going 20 years ago, actually. 2000, we're on our 20th anniversary year. So she's making the point about galactic cosmic rays are stronger at solar minimum than at solar maximum. That means that a trip to Mars is safer at solar maximum. Is that effect measurable at the ISS?
Ooh, good question. Yes, I think if you're looking at the radiation exposure, the exposure will differ of what we, basically our dose that we take on board on ISS will differ, of course, with the solar cycle. And if we're solar min or solar max, we've been coming out of a kind of a protracted solar min right now. But based on your question, Patricia, a lot of people say, hey, if the radiation is safer, background GCR is lower when we're at solar max, would we plan a Mars mission around that time? And the answer is probably not. We're probably just going to go whenever we can go, and they will accept that risk. The thing that's interesting is a lot of the question I would get also on ISS is, what if you have radiation alarms? What if an SPE event occurred? What would the crew do? We do actually have alarms. And since you really aren't able to forecast, you're kind of now casting an SPE. The crew actually talked about it, and we had large volumes of bags of water that we would each take, and we'd go into our crew quarters and surround ourselves with large bags of water to protect ourselves as best we could from any sort of large scale event.
Okay, so since we don't have a lot of time, let me get some new questioners in.
Sure.
And I'll apologize for the ones who were really keen and asked lots of questions. We might get back to a couple of them. So this is from Claire Deming. Are there plans to have similar types of microgravity research on board Gateway in a small measure or larger capacity as the ISS becomes older and possibly more obsolete? And she is regretting that fact, even the ISS.
Yeah, Claire, great question. The answer is yes. I will tell you though, the ISS itself has really expanded as a national laboratory. Just before Alex and I left in December of 2018, we installed a brand new microgravity sciences glove box, similar to the one you saw me working in the picture. So the facilities on board have really expanded. So I hope we don't stop using them anytime soon. Gateway will get there, but Gateway at first is really going to be, how do we keep the crew alive, right? For this 30 to 90 day sortie, where's the kitchen? Where's the sleep quarters? Maybe a little bit of science, but nowhere near. It's going to take time to get to what we have on ISS today.
Okay, thank you. And I'm avoiding asking you the astronomy question, but we'll jump to Don Borg Anderson's question. Chip testing for predisposition of genetics, both regarding pharmacogenomic, see, I'm out of my depth here.
Pharmacogenomic.
Yeah, you said it. Pharmacogenomic pathways and genetic germline mutations. So there's a question mark at the end of that, but I'm not sure what she's asking. So,
could you use tissue chips for that? Looking at basically, and kind of like what we talked about, Don, it's a great question. And that's, I look at, hey, how is someone predisposed to osteoporosis, disuse osteoporosis and microgravity? How would you protect them against that? How would they metabolize certain pharmacotherapies in microgravity compared to the ground? Could you pre-test them with certain agents that might work better? Absolutely. I think your ideas are great. It's probably a little further down the line, but not that far off. And no, to Marjorie, I have not seen any strange spacecraft near the ISS. Sorry.
Well, apart from the HTV, right? That's it.
Yeah.
So let me, I guess the one who hasn't asked a question yet, unfortunately doesn't have a name. It's an anonymous attendee. I think you're looking at the same screen I am. So what's the status with Robonaut?
Well, unfortunately, Robonaut and I never got to introduce myself. I did not get to introduce myself to Robonaut up there on ISS. They were not in use at that time. I want to say a portion of it has actually been flown back down to the ground. We returned it on a cargo vehicle. So as of right now, Robonaut is not currently being used on ISS.
Okay, so let me go back to Hong Yi. She's got a number of, sorry, I don't know if it's a he or she, I beg your pardon. Astronauts have to pass a lot of training before going to space. Do the animals with you feel uncomfortable during the flight? Can they get through the difficulties and still keep healthy after reaching ISS? So in other words, I guess how do the animals that you're taking up, mostly I guess rodents, respond to the flight?
This was really cool for us to watch, because certainly I feel bad. The poor little suckers have no idea when they launch that that's about to occur, and we at least get a countdown. But they all survive coming to orbit. We get them in their little habitats. We keep them at very strict temperature control. We are really following very tight regulations, IOCOOK regulations for the mice. What we got to see throughout the mission, and these mice were up there for 90 days, because we could look at them through the little screens and on the cameras. They learn how to dance and move in microgravity just like we do. At first, they're clinging on to everything very tightly, and just like humans, we grab these handrails and hold ourselves down and operate in a 2D environment. And these mice, they start running in circles around the cage, barely touching. They learn just as quickly as we do. It was actually really fun to watch them move.
So, Serena, I'd like to finish with just two questions, which are sort of a little bit more related, one to your astronaut experience and the other to the kind of some of the experiments. So Claire, who asked the question earlier, Claire Deming, how much do you exercise on the ISS, and how does that compare to how much you'd exercise at home on the ground? And don't let Jeff answer for you.
He's peeking around the corner. This is a great question, because this is a huge part of our day. 2.5 hours out of every day is dedicated to exercise on orbit. An hour and a half of anaerobic activity where we are actually lifting weights in our advanced resistive exercise device. So squats, deadlifts, bench press, bicep curls, you name it, we can do it. We use vacuum tubes to generate load up to 600 pounds. Another hour a day is spent doing aerobic activity, either on our treadmill, the T2, or on our exercise bike. So this is hard scheduled in the timeline. We do not miss it. The crew gets really upset when you cancel their exercise, because we know how important it is to bone health and muscle health to maintain strength. And when I came back, and I was within 24 hours doing rehabilitation with our specialists, they do static lift tests, and I was stronger on bench press than before I left. I was stronger on leg press than before I left. So isokinetic, just very basic, simple lifts, you're stronger. Now, you ask me to stand on one foot, not going to happen, right? So those neural pathways that basically go from the brain to all the muscles to the tendons to tell you to move and move in a coordinated fashion, those had all shut down, and they were all slowly awakening as my body relearned how to move.
And thank you. And our last question, again from Blanca, how does blood flow in microgravity, and do you have any issues with digestion?
So since the body is a whole system, just like any pumps and pipes, really, blood flows the same way in microgravity as it does on the ground. Now, the interesting thing is if you cut yourself, if it's a little tiny cut on your finger, what we call a venous bleed, the blood, instead of rapidly falling to the ground like it would here, actually pools at the site. So that's interesting because it actually obscures the site as to where the bleeding is coming from. If you happen to nick a little artery up there, that blood is going to spurt and it's going to keep going in the same direction it exited your body until it hits the wall or somewhere else in the space station. And then finally, as far as digestion, we actually had no issues. Peristalsis is kind of the body's natural way of moving food through the digestive tract, and that works absolutely the same in space as it does on Earth.
Okay, we did have a couple of other questions, and but I think in the interest of your time, I'll apologize to Hong Yi and Robert for not asking those questions. I did reply to Hong Yi's kind of astronomy question just as a text, so
okay,
it's very
no
quickly.
problem.
And Claire's saying thank you very much for amazing talk. So again, Serena, thank you very much. I know everyone appreciates your time and learned a lot, and it's always great to talk to someone who's had the kind of experiences you've had and are doing the things that you're doing to help us all, with your day job, if you like. But hopefully we'll see you in space again. And thank you again. I much appreciate the time that you've taken for us, and hope you're doing well with get your residencies in, and can keep it up with that husband of yours.
Thanks. No, David, it's great to see you. Thank you so much for having me, and hopefully we'll make it back there to Houston soon when some of the travel restrictions are lifted.
Well, you're always welcome, and maybe we'll see you online on Friday.
Perfect. Thanks, David.
Okay.
Take care.
Well, thank you everybody for joining us. Hopefully we'll see you again December 10. And again, I'm assuming you're all applauding for our speaker tonight. I think that was a really, I really enjoyed that talk, and great answers to some great questions. Yeah. So thank you, and enjoy the weekend when it comes, and we'll see you next month. All right. Thanks again. Cheers, Serena.
Bye-bye.
Bye.